Hello, we are Anita and Justin from the Data to Actionable Knowledge Lab at Harvard University, and we'll be presenting our paper, The Provinces and Pitfalls of Black Box Concept Learning Models. As a quick background, concept learning is the process of using human interpretable concepts as intermediate representations of data when training models. These representations are designed to allow humans to interpret or interact with machine learning models. For example, using concept learning, one could ask, did this model predict a positive diagnosis for Parkinson's disease because the patient's accelerometer readings indicate increased tremors? What would the model predict if the patient did not have increased tremors? It's important to be able to answer these questions when we care about model interpretability, like in the medical or legal domains. Concept learning is a useful tool for creating this meaningful interaction between humans and models. Recent work in developing concept learning models propose explicitly aligning intermediate neural network outputs with predefined concepts in a supervised training procedure. The concept bottleneck model is one such approach. It takes a standard neural network model and creates a bottleneck at one of its hidden layers. When training, a loss function is added to encourage each node of the bottleneck layer to be aligned with one of the known concepts. Training can be done sequentially, such that the model first learns to predict the concepts and then learns to predict the downstream label from these concepts, or jointly, such that the model simultaneously tries to achieve both objectives.
Unfortunately, these concept-aligned nodes, well representative of our predefined concepts, also encode extra task-relevant information. This was identified in previous work, and we refer to it here as information leakage. When information leakage happens, we say that the concept representations are not pure. In our running example, for each patient, the concept of has increased tremors is either true or false, but the outputs of neural network nodes are never exactly 0 or 1. For instance, the network may produce probabilities that a patient has increased tremors, like 0.02 or 0.98. Because these probabilities are all close to their corresponding binary labels, it's tempting to think of them as just conveying the fact that the increased tremors concept was true for a given patient. But what does the deviation from the binary labels encode? It turns out that this deviation can contain a lot of information relevant to the downstream task. If the activation of a concept-aligned node represents both the concept and other task-relevant information, interpreting the node as if it represents only the concept can be misleading. For example, the Parkinson's prediction model may use probabilities like 0.02 or 0.98 very differently than the binary concepts, the zeros and ones, when making a diagnosis. Thus, the fact that the predicted probability of increased tremors is highly indicative of Parkinson's disease may not imply that there is a significant correlation between increased tremors and Parkinson's in the data. In our paper, we investigate a number of natural mitigations against information leakage. We use sequentially trained models to look at learning the concept representations without knowledge of the task. We look at leaving extra non-concept aligned nodes in the concept representation layer. The hope is that the extra information moves to those nodes, leaving our concept aligned nodes more pure. And finally, we look at encouraging the nodes to be decorrelated through concept whitening. We find that none of these three fully prevent task-relevant data from leaking through. We'll go into detail on the first two approaches here. First up, sequential training lets us train the concept representations without knowledge of the task. Let's walk through an example. We start with a curated subset of MNIST, which contains handwritten digits. The goal is to predict whether or not the depicted digit is even. We're provided with two concepts, is 4 and is 5. These are binary concepts that indicate whether or not each image depicts a 4 or a 5. On the surface, these concepts appear related to the task. If we know the image depicts a 4, we know it's even. If we know it doesn't depict a 4, we know it's more likely to be odd. But for this example, we're going to consider an extreme case where there are no instances of 4s and 5s in our data set. The only digits that appear are 0, 1, 6, and 7. Thus, these two concepts are totally irrelevant for the predictive downstream task. We have 500 examples of each digit, so if we base a model solely on our completely uninformative concepts, we should expect to see 50% accuracy when trying to predict the parity. But what happens if we try to learn the concepts anyway, and we build a model to predict parity based on these learned concepts? Will our predictive downstream model perform as expected? To find out, we build a two-part concept bottleneck model. The first part is a neural network that predicts our concepts. When training, we align each bottleneck node with one predefined concept so that each node is predictive of one concept label. The second part is a neural network that takes the output of the bottleneck layer and predicts the downstream task label. We train the features to concept part first. This learns the concept labels from the images without any reference to the downstream task. This prevents the bottleneck nodes from being incentivized to encode any additional task information. When predicting concept labels from the images, our bottleneck nodes output probabilities, that is, soft representations of the concepts. We then train the concept to task part to predict parity from our soft concept representations. The result is that the concept to task model achieves 69% test accuracy when predicting parity. Shockingly, this performance is far better than if we try to predict the parity from the true binary concept labels, where we achieve the 50% as expected. So, where does this predictive performance of our soft concept representations come from? It turns out that although the concept themselves are completely irrelevant to the predictive downstream task, the soft concept representations encode the geometry of our data distribution. And that geometry is very useful for the prediction of parity. The surprising observation is that this information leakage happens even when the concepts are learned without any reference to the downstream task. In our paper, we explain in detail how this information leakage occurs and why leakage is a serious problem, even for task-blind training of concept learning models.
Now, going back to our running Parkinson's disease example, while we know that increased tremors is a relevant concept that can be extracted from accelerometer readings, as it is often the case, neural network models can pick up other useful concepts from the data that we are unaware of. For instance, the model might notice a particular tremor pattern in patients with Parkinson's disease while walking compared to other patients. Having an incomplete concept set can diminish a concept bottleneck model's performance compared to a standard model that predicts labels from features. It can also be a possible cause of compromised purity of the bottleneck nodes as the model tries to leak the missing information through the bottleneck dimensions to help with the downstream task prediction. So one might think that impurity issues with concept learning models can be resolved by introducing latent dimensions in our concept bottleneck that allow missing information to be extracted from the features without compromising the purity of the known concepts. To investigate how effective this solution is, we set up a data set of points in 3D space. The coordinates of these points are normally distributed about 0. Each of these points are labeled as orange if at least 2 of the coordinate values are positive. Otherwise, they're labeled as blue. We aim to predict these color labels from a set of 7 features that are non-invertible transformations of the coordinate values, since one might think of low-level features that are typically used for training neural network models as complex transformations of more interpretable concepts that are relevant to our prediction task. We specify 3 relevant concepts that fully capture all the information needed for predicting the color labels. These concepts are x plus, y plus, and z plus, and specify if the corresponding coordinate values are positive. We take x plus and y plus to be our known concepts and z plus to be the unknown concept. We set up a concept bottleneck model that has a bottleneck layer with 3 dimensions. The first 2 dimensions are each trained to predict the known x plus and y plus concepts, and the third dimension is left latent to allow other information related to the unknown z plus concept to go through. For this model to be interpretable, each of the bottleneck dimensions have to purely represent a single concept. We investigate this by quantifying how predictive each bottleneck dimension is of each of our 3 concepts. Unfortunately, we observe that introducing the latent dimension does not help improve concept purity. All the aligned bottleneck nodes are still partly predictive of the concepts that they were not aligned with. The latent dimension does not align with the missing concept. In fact, the latent dimension further compromises interpretability by also leaking information about the known concepts. To recap, we have shown that information leakage is a persistent problem in concept learning models which cannot be resolved by straightforward approaches such as sequentially training the model, introducing latent dimensions for missing concepts, or decorrelating bottleneck dimensions during training. Future research should try to explicitly enforce mutual exclusion among aligned and unaligned bottleneck dimensions and utilize domain expert supervision in training concept learning models. Thank you for listening to our presentation.